Welcome to the deep dive. Just take a moment and think about it. Generative AI, large language models, these aren't just tech buzzwords anymore, are they?
No, not at all. They're really becoming part of our daily lives.
Exactly. They're woven into how we use technology, how we create things, maybe even how we think. But, beyond the flashy demos and viral stuff, there's a really crucial question.
Mm.
How do we actually build these incredibly powerful systems, like responsibly, effectively, and at the massive scale we're seeing? What are the real principles, the tools driving this whole revolution?
Well, that's exactly what we're diving into today. We're drawing insights from this NCA-GENL exam practice document. It's all focused on generative AI and LLMs.
Okay.
Think of it as a shortcut, maybe, a path to understanding the core ideas, whether you're, totally new to this, or maybe just want to solidify what you already know, or if you're just curious about how this cutting-edge tech actually ticks.
That's it, precisely. Our mission here is really to distill the most important bits of knowledge from these sources, give you that shortcut to being genuinely well-informed about the critical stuff, technical and ethical considerations in AI today.
Right.
We're not just listing definitions. We want to unpack the big challenges and also some of the really clever, sometimes groundbreaking solutions being used right now. We'll look at the foundations of trust and the amazing engineering that makes it all work.
Okay, so let's start unpacking this with, well, a really fundamental idea, trustworthy AI. We hear that phrase thrown around a lot.
Yeah, we do.
But what does it actually mean when we're dealing with systems that can generate, super convincing text or images, systems that are powerful but often kind of black boxes? It's got to be more than just marketing speak,
Oh,
right?
absolutely. It's definitely not just a buzzword.
Yeah.
It's really a critical framework.
Yeah.
And one of the absolute pillars, maybe the bedrock, is reliability.
Reliability. Okay. Yeah. And this isn't just like, does the code run? Does the system turn on? Reliability here means the AI system's consistent ability to operate as expected, predictably,
Yeah.
even under all sorts of messy, real-world conditions.
And so not just in a clean lab setting.
Exactly. Think about an AI in, say, medical diagnosis or managing finances. It might be super accurate in the lab, but real reliability means it stays accurate even with noisy data, incomplete information, or sudden changes in the environment it's working in.
Right.
It's about being robust, stable, making sure the AI doesn't just fail or give wildly different answers when things get unpredictable.
Yeah.
I mean, if you can't rely on it to be consistent, how can you trust it?
That makes perfect sense. So it's not just if it works, but how consistently it works, even when things are chaotic. Okay. But even a really consistent system could make a decision with huge consequences. Which kind of brings us to accountability, right? Who's ultimately responsible when an AI does something? What's that mean for, human oversight?
Exactly. Accountability is kind of where the rubber meets the road, beyond just the tech performance. In this trustworthy AI framework, accountability is mainly about the legal and ethical responsibility for what the AI does, its actions, its decisions.
Legal and ethical, got it.
Yeah. It's about making sure that humans or organizations are clearly still in charge. They're ultimately responsible for the outcomes. This covers things like governance, following regulations, defining liability clearly.
Okay.
And what's interesting is it pushes us beyond just the engineering side. It forces us to think about the societal impact. Who sets the rules? Who approves deployment? Who deals with the consequences if it goes wrong? It's really about keeping human control and ethical oversight in this increasingly automated world.
Okay, that sounds like a pretty thorough way to build trust. But here's where it gets, really interesting and maybe a bit concerning for a lot of people. We've all seen those examples, right? Maybe even experienced it, where an LLM just seems to make stuff up.
Oh, yeah. Hallucinations.
Yeah, that confidence, but it's just fiction. It's really something, isn't it?
It absolutely is. You're talking about hallucination in LLMs. And the really tricky part isn't just that it's wrong. It's that it presents these fabrications with such conviction. They sound so plausible, so fluent.
They sound totally real.
Exactly. It makes it incredibly hard for a person to spot the error. It's not really a bug like in normal software. It's more like an emergent thing from how they learn language patterns. They sometimes just generate stuff that sounds good, but is totally false.
Wow.
And that's a huge challenge for trust, especially if you want to use LLMs for things where facts really matter, legal advice, medical info, news. You need to know it's not just well-written, but actually true.
So, okay, if the models can be so convincingly wrong, how are developers trying to put, guardrails on them? How do you steer them towards being safer, more aligned with what we want, and stop them from telling these digital fairy tales.
Yeah, that's a massive challenge, and that's where you need sophisticated tools. One of the key ones people are using is NVIDIA NeMo guardrails.
Nemo guardrails. Okay.
Its main job, basically when you're building an LLM app, is to enforce safety policies, to steer the LLM's behavior.
How does it do that?
Well, imagine you're building, say, a customer service AI. NeMo guardrails can stop it from answering questions it shouldn't, like things outside its topic. It can prevent it from generating toxic or inappropriate stuff. It can even make sure it follows a specific conversation flow, like, if you can't answer, hand off to a human.
Ah, okay, so it's like setting boundaries.
Precisely. It gives you this configurable layer of control, keep the model on topic, stick to ethical rules, make sure its answers fit what the company or user actually needs. It's about giving us tools to manage these incredibly powerful, sometimes unpredictable models.
That sounds crucial. Nemo guardrails, keeping an AI on script, sort of. Okay, let's shift gears a bit. We've talked trust, behavior, but what about the real nuts and bolts, the physical security of all the sensitive data these models use?
Right.
You're feeding huge amounts of private or company data into AI for training or just processing. How do you make absolutely sure that data stays private, safe, even from other parts of the system or, a hacker?
That's a great question. And it takes us into confidential computing. And what's really fascinating here is the idea of using secure enclaves.
Secure enclaves, like a vault?
Kind of, yeah. Think of it like a highly secure vault, but built right into the hardware for your data and code.
Okay.
The sensitive data and the code processing it, they get loaded into this secure enclave. And the key thing is, even if the main operating system or other apps or even a system admin tries to look inside or mess with the data in there, they just can't.
Wow, really?
Yeah. It guarantees confidentiality and integrity. Your sensitive data stays private and unchanged, even if the rest of the system outside that enclave gets compromised. It's a really big deal for privacy in sensitive areas, like healthcare records or financial AI.
A digital fortress. That sounds incredibly secure. But I guess that isolation might make things like debugging tricky. Anyway, these models, they're also just enormous, right? Billions, trillions of parameters.
Absolutely massive.
It feels like trying to fit a skyscraper into a shoebox. You just can't train something that huge on one computer, can you? So how do the AI architects actually solve that scaling problem?
Yeah, you've hit on a huge challenge. And the solution involves some really clever parallelization. One key technique is pipeline parallelism.
Pipeline parallelism. Okay, break that down.
So instead of trying to force the whole model onto one GPU, you distribute the layers of the giant neural network across multiple GPUs. Think of it like an assembly line. Each GPU in the pipeline works on a different segment, a different set of layers. Data flows in, gets processed by GPU 1, the results pass to GPU 2, then GPU 3, and so on.
Got it. Like passing work down the line.
Exactly. And this lets you train models that are way too big for any single GPU's memory. It's absolutely essential for scaling up to those giant models that are pushing the boundaries of AI right now. Without stuff like this, large-scale AI just wouldn't be feasible.
That's a really smart way to tackle an impossible-seeming task. So, okay, you've trained this massive model using pipeline parallelism. Now the next challenge. Making it run super fast and efficiently for actual use. Training is one thing, but inference, getting predictions out quickly, maybe thousands a second, that's different.
It's a completely different beast, yeah.
How do they optimize for that? Make AI practical for real-time stuff.
That's where optimization for deployment is key. And tools like NVIDIA TensorRT come in. Think of TensorRT like a high-performance tune-up shop for your trained models.
Okay, mechanic for models, I like it.
Yeah. It takes your model and applies a bunch of optimizations specifically for inference speed. For instance, it often converts models to lower precision, like FP16.
Lower precision, like less accurate.
Not really perceptibly less accurate for most tasks, but much more efficient. Imagine an artist using a slightly smaller paint palette, maybe 65,000 colors instead of millions. The final picture looks just as good to most people, but they use less paint and finish way faster.
Okay. Good analogy.
TensorRT also does things like layer fusion, combining multiple small steps into one bigger, faster step, and kernel auto-tuning to optimize the calculations for the specific hardware. All this makes inference much faster and uses fewer resources, usually without any real hit to accuracy. It turns a powerful but maybe slow model into something fast enough for real-time use.
Fantastic analogy, making them lean and mean for the real world. Okay, but what about when you have tons of users or lots of apps all hitting their optimized AI model at the same time. How do you handle all those requests efficiently without everything just slowing to a crawl?
Right, you need to max out the hardware efficiency, and that's where something like the NVIDIA Triton inference server and its dynamic batching feature really shines.
Dynamic batching. Okay, what's that?
Imagine a busy kitchen again. Instead of the chef cooking every single order the second it comes in, which might be inefficient.
Yeah, lots of starting and stopping.
Exactly. Dynamic batching is like the chef waiting just a moment to see if a few similar orders arrive quickly. Then, they group those individual orders, those separate client requests, into one larger batch that can be cooked much more efficiently together on the GPU.
Ah, so grouping similar requests.
Yes. This strategy seriously boosts GPU utilization and throughput. The GPU works harder and smarter, handling more requests in less time, which ultimately lowers the latency for everyone. It keeps things smooth, even when it's really busy.
Makes sense. Keep the expensive hardware busy doing useful work. So it's clear building and deploying takes cutting-edge techniques. But let's zoom out a bit to the whole AI ecosystem.
Okay.
Where do developers actually go to find the resources they need, the pre-built stuff, the tools,
Yeah.
so they don't have to reinvent the wheel every single time?
That's exactly the problem the NVIDIA NGC catalog aims to solve. Yeah. Think of it as a central, curated library for AI developers.
The library. Okay.
Yeah. It's got tons of GPU-optimized containers, basically, ready to run software packages. It has pre-trained models, sometimes even industry-specific AI solutions all ready to go.
So it speeds things up considerably.
Hugely. It simplifies the whole process of building and deploying. Instead of spending ages setting up software or training basic models, developers can just pull down tested, high-performance components. It lets them focus more on the unique parts of their project, on innovation, rather than just the infrastructure. It really helps democratize access to these powerful tools.
Sounds super helpful for getting projects off the ground quickly. Okay, last area then. We've got all these different AI frameworks, PyTorch, TensorFlow, JAX, others. It can feel a bit like a scattered landscape.
You can, yeah.
What if you train a model in one framework, maybe optimize it with specific tools, but then you need to deploy it somewhere totally different on different hardware or using a different system? How do you make sure things can actually talk to each other? Avoid getting locked into one vendor.
That really hits on a crucial point for the future of AI flexibility, open innovation. And a key part of the answer is the ONNX format. ONNX stands for Open Neural Network Exchange.
ONNX. Okay, Open Exchange.
Exactly. Its main goal is to be a standardized, open-source format for representing deep learning models, like a universal language for models.
The translator.
Precisely. So you could train your model in, say, PyTorch, export it as an ONNX file, and then reliably run that exact same model in an environment optimized for TensorFlow, or maybe on some edge device that supports ONX.
Ah, that's clever.
It ensures interoperability, smooth deployment across different frameworks, different hardware. This open standard is vital because it lets developers choose the best tools for each job, training, optimizing, deploying, without being stuck in one single ecosystem. It really helps foster a more open and collaborative AI world.
Considering all these advancements trying to make AI safer and better, what ethical or societal challenge are you, listening out there, most hopeful that these improvements will help us solve? Or maybe, what new challenge might they accidentally create that we need to watch out for? What specific part of AI's future are you going to be keeping a close eye on? Thanks for joining us on The Deep Dive.